In the last video, we introduced Newton's first and second laws of motion, and at the end I mentioned that there is a little bit of a subtlety about mass that I need to get into. So let's go ahead and delve into that, and then in another couple of videos later in this series, we'll explore how that leads to saying that acceleration in free fall is always a certain number. So to go at it here, let's start by trying to figure out how we could measure the mass. And there are ways we can do this. There are practical measures for force that we can use. Here's DSE. Yeah, there we go. And one example of this is we can use a property called elasticity. Turns out that properties with elasticity tend to exert forces that are proportional to how much the object itself has been stretched. So for instance, a spring. If I have a spring and I pull on both ends with some force F, the spring will stretch, and the amount of that stretch, delta x here, turns out to be proportional to the force applied. Later we'll get into that more rigorously when we explore simple harmonic motion and we take a look at Hooke's law. But for now, I just want to point out that this is a property that springs have, at least within a certain range of their use. So what we could imagine doing is taking a motion detector, and we can load up a dynamics cart and make that dynamics cart have a mass of 1 kilogram. Or we could even do something like go and grab one of those spheres of silicon that have been used to create our reference masses, or we can go buy a calibrated kilogram from Ohaus, something like that. Somehow we get a kilogram that we know is a kilogram. And then we can apply a spring to it, and we can pull on the spring with some force such that it accelerates at 1 meter per second squared. We can measure how much it stretched, and we can observe that the force would have been 1 kilogram times 1 meter per second squared is a Newton. And then we could repeat this process. So we again take our calibrated kilogram and we apply some force to it. But now, instead of making it accelerate at 1 meter per second squared, we make it accelerate at 2 meters per second squared. And we'll observe that it stretches twice as much as before. And we would note that that force would be 1 kilogram times 2 meters per second squared is 2 newtons. All right. So we can take our reference kilogram and we can keep applying a whole sequence of different forces with this spring, determining the force that had to have been applied to make that acceleration happen, and then measure how much the spring got stretched each time. And we can use this until we have enough calibration points for the spring to show ourselves that, yes, it's operating in its elastic regime. And then we can go ahead and just mark this much stretch is 1 Newton, this much stretch is 2 newtons, and so forth. Okay. So once we've done all that, this gives us a recipe for measuring what I'm going to call the inertial mass, because it turns out that there are two different kinds of mass. So now what we can do is, again, use our motion sensor. But now we will drag an unknown mass using a sequence of known forces. So we first calibrated our force measurement device, our spring, by taking a known mass and pulling at it until we had known accelerations. And now that we have that, we can apply a sequence of known forces using our calibrated spring. And we will get a sequence of accelerations. And when we plot it out, there we go. If I plot the applied force on the y-axis and the acceleration on the x-axis here, or on the vertical axis and the acceleration on the horizontal axis, and don't bust my chops about, aren't you always supposed to put the manipulative variable on the horizontal and the responding variable on the vertical? That is a convention in other fields of science. In physics, what we often do is we take a look at our key relation here. So we're testing A equals F net over M, which is F over M. And when we rearrange that, we get F equals MA. Now, since we want to get the mass, if we write it this way, we look at this and realize that mass is the slope. So physicists are willing to bend the rules about which axis has the manipulative variable and which has the responding variable in the name of mathematical cleanness. So that's what we're doing here. So we'll go ahead and we'll plot it off, and what you're going to find is you're going to have a bunch of scattered points, but they'll be scattered around some line. And we can go ahead and measure the slope of that line, and that would be the mass. And specifically, this would be the object's inertial mass. So this is characterizing here, how hard is it to change an object's velocity. Okay. This is distinct from measuring what it's called the gravitational mass. Which this is the actual official definition. The official definition that where the current recommended best practice, or I should say the current recommended best practice, because the official definition is to make Planck's constant an exact number. The current best practice for measuring mass is to use a device called a Kibble balance, or it's also known as a Watt balance. And this turns out that conceptually what you're doing is not a lot different than what the old definition was, where you'll put your unknown object in one pan and you'll put your known object in another pan and you'll let them balance on a balance beam. Now here, in the new definition, this known object is no longer a known object. It is a known electromagnetic force. But still, the idea is the same. So here, if you think about it, we were not really measuring the mass. We're comparing forces. In fact, it's even more blatant with the new current recommended best practice. You're looking at the force of gravity exerted on the mass here. And in the old definition, it would have been comparing it to the force of gravity exerted on a copy of the prototype of the kilogram. And in the new best practice, it would be a magnetic force. But either way, the point is you are comparing forces. So when we do this and we set up this weight and we say, yeah, this has a mass of 1 kilogram, well, that isn't the same thing. This is measuring how hard, or how much, I should say, gravity interacts with an object. So, what gives? So these are different things, but yet we use the same letter M for both of them. And this is because it's just a statement of experimental observation. It appears, and emphasis on appears, that the inertial mass of something is also equal to its gravitational mass. There have been experiments done where they have simultaneously measured the inertial and gravitational mass of an object. And the best experiments that I'm aware of, if the difference between the inertial and gravitational mass were greater than 1 part in 10 to the 8, so 1/10 billionth, the experiment was sensitive enough that it would have noticed that. So that's not saying that the experiment showed equality, but it showed that if there isn't equality, the difference isn't very big. So what this means is we're going to go ahead and assume equality. But keep in the back of your mind that the M and A equals F net over M, that's the inertial mass. And when we put together a model of gravity in 2 videos, we'll say that the gravitational force acting on something is mg, where little g is the gravitational field strength. This m is the gravitational mass. We will treat them as if they are the same quantity because it appears they are. However, this is an experimental statement. Einstein took this idea and ran with it to develop his model of gravity, which we call Einstein's general theory of relativity. So it's one of those things that certainly looks like they're the same, and we're testing very carefully to see if there's any difference, but it appears that there is not. So we just go ahead and assume equality on these. And in a couple of videos, we'll explore some of the consequences of that. Alrighty. So in the next video, we will go ahead and tackle Newton's third law of motion.